Next topic is velocity of electron in Bohr stationary orbit. Velocity of electrons in Bohr stationary orbit. As we know, electrons revolve around the nucleus due to electrostatic force of attraction which provided the centripetal force. That means centripetal force mv square upon r, that is equals to k, that is 1 by 4 pi epsilon naught, z charge on the nucleus, charge on the electron divided by r square. From this we get r is equals to kze square upon mv square. Let this be equation 1. And according to the Bohr quantization condition, mvr equals to nh upon 2 pi. From here we get r is equals to nh upon 2 pi mv. Let this be second equation. Now comparing 1 and 2, by comparing 1 and 2, we get this equals to this. So what we get here? K z square upon mv square equals to nh upon 2 pi mv. So by solving this we get velocity is equals to 2 pi k e square by nh. This is the value of the velocity of electron orbiting around the nucleus. So it's also depend on n. We can also write it as n is Vn equals to, where n is the principal quantum number, k e square by n h, where k is 9 into 10 raised to power 9 Newton meter square per coulomb square. Value of E is 1.6 into 10 raised to power minus 19 coulomb. H is 6.63 10 raised to power minus 34 joule second, and the value of n, that is equals to principal quantum number, that can be 1, 2, 3, 4 so on depending upon the orbit. Next is frequency of electron in Bohr stationary orbit. In Bohr stationary orbit. How to calculate the frequency? As we know, there is a relation between the linear velocity and angular velocity, that is v equals to r omega, and this angular velocity is nothing but 2 pi into linear frequency. So from here we get f is equals to v upon 2 pi r, where velocity is nothing but it is 2 pi k z square upon nh into this 2 pi r. So by solving this we get frequency is equals to kze square upon nh by r. It's also depend upon n. So this is the frequency of the orbit revolving around the nucleus. So from here we can say frequency is inversely proportional to n. Frequency is inversely proportional to n. It means more the value of orbit, lower is the frequency. Lower the value of orbit, more is the frequency. Next is total energy of electron. Total energy of electron in Bohr stationary orbit. We have to find expression for that. We know that total energy is equals to kinetic energy plus potential energy. So we have to find kinetic and potential and substitute the value here. We get the total energy. Where kinetic energy from this relation mv square upon r equals to kz square upon r square. If I multiply both sides with r, this r get cancelled with r. This is what? This is kinetic energy. So from here I get kinetic energy is equals to half k z e square upon r. That is kinetic energy is equals to k z e square upon 2r. Where potential energy is equals to, that is minus of charge into potential, that is k z square upon r. Now total energy is equals to kinetic plus potential, and if we substitute the value we get k z square upon 2r plus minus of k z square upon r. From here we get it is equals to minus k z square upon 2r, where minus sign shows that that system is a bounded system. By substituting the value of r, we get r that we have found for the Bohr's orbit. We get energy is equals to, as r is equals to n square h square 4 pi m k pi square k z square. By substituting that value we get total energy is equals to minus of 2 pi square m. I'm writing it again. Total energy is equals to minus of 2 pi square m k square z square e4 whole divided by n square h square. So if we calculate it for hydrogen atom, it will be, for hydrogen z is equals to 1, it will be total energy. After calculating all this value, you will get a result that is minus 13.6 z square by n square. So it is inversely proportional to n square. So we get total energy for hydrogen atom, that is minus 13.6 by n square. If we calculate the first orbit, that is minus 13.6 in electron volt. This is in electron volt. Here we can see that energy is inversely proportional to n square. It means spacing between energy level keeps on increasing at discontinuous pace or square pace.